Welcome to independent events. We're going to be doing most of these problems today with a two-way table. So for the do now, a person flips a coin and notes that it comes up heads. Then the person rolls a standard six-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 dependent on getting a head when flipping the coin? If you think about it, flipping a coin has nothing to do with rolling a die. So no, one is not dependent on the other, because whatever you get on the die, it doesn't matter what you got on the coin flip before that. So no, because they have nothing to do with each other. So that's what we're really going to be working with today. Does something happening depend on something before that also happening? And if it does depend, then we call it, dependent. Otherwise, it would be independent. So for the next example, a survey of 57 sixth graders was done to determine which subject was their favorite, and the results are shown below. They want to know what is the probability that the student is female. So nothing fancy about this question. They just want to know basic probability, which means your total is going to be the overall total of 57. Out of those 57 people, 30 of them were female. Now, for the next one, we're saying, given that is your keyword, that the student prefers math. So this is your condition, and that means math should be your denominator. What is the probability that a student is female? So going over to the math section, only looking here, of those 18 people who have a favorite subject of math, 8 of them are female. Next one is also conditional probability because they mention the word among, and your condition is still among the students who prefer math. So same denominator, and you're still looking at this section. What is the probability that a student is male? There are 10 out of 18 students who prefer math that are male. Now let's go over some new definitions. Two events are independent when knowing that one event has occurred does not change the likelihood that the second event has occurred. So for example, your do now. Now, two events are dependent when knowing that one event has occurred changes the likelihood that the second event will occur. For example, choosing 2 cards from a deck. If you take a card out of a deck the first time, and let's say you get a ace of spades, that means the second time there is a 0% chance of getting a ace of spades because you just took it out. So that second draw, your probability changes because you now took one card out of the deck from the first one. Now, there are rules to test to see if two events are independent or not. So those rules are not on your reference table. You do have to remember these. Now, there are conditional rules, and then there is the multiplication rule. So for the conditional rules, it's that the probability of A given B has to equal the probability of A. Or you can switch the letters. The probability of B given A has to equal B. Notice that what comes before the condition has to also be by itself. And these are tests to see if it is independent. So if the left equals the right, that means it is independent. If the left is different than the right and they are not equal, that means that the two events are not independent, that they are dependent. For example, if we talk about the probability that I will go on a walk, given that it is raining out, versus the probability of me just going on a walk. Now, I'm a lazy person. I do not like to walk, so my probability of going on a walk is probably about 20%, right? However, the probability that I'm going to go on a walk when it's raining outside is 0. So because both of these probabilities are not equivalent of each other, we're going to say that they are dependent events. That means that walking and the probability of it raining are dependent. A good example of independent events are me having breakfast and it raining outside, because the likelihood of me having breakfast doesn't depend on if it's raining or not. I'm still going to choose to eat based on if I'm hungry or not. I don't care about what's happening outside for that. Now, the other formula is the multiplication rule. So the probability of A times B has to equal the probability of A and B together if it were to be independent. You might also see this rule written as P of A and B with the upside down U. Remember that A is equal to and, the union. And if you're not good at remembering the symbols, think of it as an A. If you put a line through it, it could kind of be made to look like an A. So let's try an example. We have Sean's team has a baseball game tomorrow. He pitches 50% of the games. So the probability of him pitching is 0.5. There is a 40% chance of rain during the game tomorrow. So we have the probability of it raining is 0.4. If the probability that it rains given that he pitches. So we have rains given pitches. And they're telling us that is 40%. It could be concluded that these two events are blank. Now, mutually exclusive means that they cannot happen at the same time. If you think about it, he can pitch while it is raining. So because those two events can happen at the same time, they are not mutually exclusive. We know that complements are basically it happening and not happening. So pitching and not pitching are complements. Also, when you add the probability of complements together, it will equal 1. So it's not complements either. If you use some logic, it has to be 1 or 2, because your answers are either independent or dependent. There is no other option. So it has to be one of them, because one of those definitely has to be right. So this problem is just about, do you know the formula and what to use? So remember in the formula that what comes first before the condition has to be by itself. So rain comes first before the condition, so we're looking for the probability of rain by itself. So what we're looking at here is the probability of raining given that he pitches, is equal to the probability of just raining. So the probability of raining given he pitches is 0.4. The probability of just raining is also 0.4. They are equivalent, which means they are independent because the probability of the first does not change when given the condition of the other. Also, if you just thought about it, it doesn't make sense that him pitching would affect the probability of it raining. So just logically, they have to be two independent events. Let's try examples with two-way tables. So determine if the two events, a randomly selected student has asthma and a randomly selected student has a household member who smokes, are independent. And always remember, when you're talking with two-way tables, you want to define your events before using them in the formula. This not only helps you stay organized, but it helps your grader on the regions and me on tests stay organized as well, because if I can't figure out your work, then how are you getting credit for it? So let's make event A being a randomly selected student has asthma. And let's make B be a randomly selected student has a household member who smokes. Now, it doesn't matter if you chose to swap your A and B, like doesn't matter what you call A and what you call B. You also don't have to write it out in complete sentences. You could have made A be having asthma and B household member who smokes. You can simplify it for yourself if you like. You can do these problems two ways. So you can choose the multiplication rule, or you can choose the conditional rule. The choice is yours. Let's try using the multiplication rule first. Now, for the multiplication rule, we have the probability of A. So the probability of having asthma is 182 out of the total of 937 people. Times the probability of B, which is it's going to be 395 out of the 937. Now, we're trying to see if that's equivalent to A and B happening at the same time. A and B is going to be 113 people out of the 937. Now, you're going to put the right-hand side, well, let's start with the left-hand side. Do 113 divided by 937. We can't really compare the fractions when they're as fractions, so we're going to make them as decimals by actually dividing it. If you use alpha y equals in your calculator, it's only going to simplify the fraction. It's not going to convert it to a decimal. So actually use the division button. 113 divided by 937. You should be getting 0.1205 and so on. Now you're going to put the second one in the calculator. If I were you, I would use alpha y equals first to multiply the two fractions, and then divide the fractional answer that you get. If you want, you could put this in as 182 divided by, with the division sign, 937 times the other one. But if you choose to do that without alpha y equals at first, please make sure that you use parentheses, because if you don't use parentheses, it's going to mess up. You should be getting 0.0818. Now, these are not equivalent, so your answer is not independent. Or you could write that it is dependent. Choice is yours. Now, if you didn't like doing it this way, you can use the conditional rule. If you have trouble finding conditional probability from a two-way table, I suggest you don't do this. So the conditional rule, the probability of A, we already figured that out, right, from here. And the probability of A was 182 divided by 937. Now finding the conditional probability. We're talking about your condition being B, having at least one household member who smokes. So this. The conditional probability of A given B is going to be 113 out of the 395. Anyway, when you put both of these in the calculator, you get 2860, which is 0.194. They're not equivalent, so you end up with the same exact answer as before. So if you know both formulas, it does help, because if you do it both ways, you should be getting the same answer, and it's a good way to check your work. You can choose either way you'd like, though, when you're given a two-way table. Personally, I prefer the one on the right because it's easier to put in on the calculator. But again, only do that if you're good at conditional probability. Let's try another. So we have the following hypothetical 1,000 two-way table was introduced, and they gave us one for this group of people. Do these data suggest that watching the online ad and planning a vacation to New York in the next year are independent? And they want you to justify your answer. First things first, actually write what's what. So we have A, which is watching the ad. And we have B, which is plan a vacation. And go and write that in for yourself. So let's do it the conditional way first this time. So for conditional probability, we have the probability of A given B is equal to the probability of A. So the condition B was planning a vacation. So we're looking here. Now, the probability of watching an ad, given that they plan a vacation, is 300 out of the 400. And the probability of just A is not 300, is 750 out of 1,000. If you put these in the calculator, you should be getting 0.75 is equal to 0.75. So because these two are equal, this is independent. Trying it with the multiplication rule. So we have the probability of them both happening, A and B, is equal to the probability of A times the probability of B. So let's erase this. The probability of A and B. We have the intersection is 300 out of 1,000. The probability of A we already determined over here is 750 over 1,000. And the probability of B. There are 400 people who are planning a vacation out of the 1,000. If you put that in the calculator, you should be getting 0.3 is equal to 0.3. They are equal to each other, which means they are independent. Two different ways, same answer. If you really wanted to, you could have also done the probability of B given A is equal to the probability of B. I don't know what you get, but I do know that they would be equivalent and be independent. Now, why do companies actually do this and look at independence? Well, if you're talking about watching an online ad and the probability of planning a vacation, if you know that those two probabilities have nothing to do with each other, what's the point of spending money on an online ad, right? Because ads are supposed to make you more likely to actually plan a vacation. So, in theory, watching the ad and planning a vacation should be dependent, right? Your probability of planning a vacation should increase if you watch the ad. But that's not the case here. So, this was a very poor online ad. And the last example. So we have the results of a poll of 200 students, and North Caldwell High School about music preference are shown in the table below. So they want to know, are the events student is a female and student prefers rap independent of each other, and they want you to justify your work. Keep in mind that justify only means to show work. You don't have to write a sentence explanation for this. So we have that A is being a female, and B is preferring rap. Remember, you could also make A be rap and B be female. I don't care, same thing. So we have A and B. You don't have to label the table, I just think it's helpful. When you're looking at this table, you should notice that your totals are missing, so you should go and input them. If you're having trouble with finding the totals, refer back to the Intro to Probability video, and it will explain how to go over them. So let's start with conditional probability. We have the probability of A given B is equal to the probability of A. And remember, my keyword here for using these formulas is independent. Anytime you see this word, you should be writing these formulas down and be prepared to use them. So if you're looking at your condition of B liking rap, that's this column. And we have that 25 of the 65 people who prefer rap are female. Then you have just the probability of being a female. Oops. So now let's look at just being female. And there are 27 out of, there are 106 total females out of 200. Put them in the calculator, and you'll see that the fractions are not equivalent. So because they're not equivalent, you're going to say that they are not independent. Or again, if you prefer, they are dependent. Now for the second one with the multiplication rule, we have the probability of A and B equals the probability of A times the probability of B. So the thing with probability is each individual probability problem is not too difficult, but remembering all the formulas and all the different types of probability, that's where it starts to become a little bit challenging. So the probability of female and rap, you have an intersection of 25 out of 200. The probability of just being female, we already found, is 106 out of 200. The probability of just liking rap music is 65 out of 200. And if you were to put this in the calculator, you'll see that the left does not equal the right, so you get the same exact answer as before. And these are usually 2-point questions on the regions. So let's sum it up. Independent events. There are 2 tests. Remember, you have the conditional test. Just keep in mind that what comes first before the slash has to be by itself. And if these work, if they are equal, then they are independent. If they are not equal, then they are dependent. The second one is the multiplication rule, where you have the probability of A and B is equal to the probability of A times B. Keep in mind when you use this in the calculator to use parentheses, that way none of your denominators get mixed up, or just use alpha y equals. And the same thing stands. If they are equal, it is independent, not equal, dependent, and one affects the other. Now, when it comes to two-way tables, you can choose either rule that you like to use. It's up to you. In the next video, you're going to see all these problems where they don't give you two-way tables. And if it's flat out just a word problem, you have to use the information that they gave you. So that one's going to be either or. You have to remember both of these formulas because in those word problems, it's one or the other. You don't get a choice. Two-way tables, though, it's nice. Use your preference. And that's all for this video.